you need to consider a different what? You need to consider the period that is above. So if you consider the period above oxygen there, you're going to find that the noble gas that is there should be helium, if I'm not mistaken. Not so.
Yes, there is helium.
So the way you're going to write it, you say helium like that. So helium has gotten how many of your electrons? It has gotten how many? It has gotten 2 electrons. So basically, if you have something big, of course in this case you'll be able to say, okay, I think it's going to be 2s2 2p4, what is remaining. You show it like that. But that is kind of a thing, like it's more like you're cheating by looking at that. So we don't want you to do that. How about if they give you something big? How are you going to be tell, like, okay, this is what I'm going to use? So from the same oxygen, if you check oxygen is in period what? Oxygen is in period what? Period 2, right? So you just say helium, then you ask yourself, where is oxygen? Oxygen is in what? Oxygen is in period what? What are we saying? So we are saying oxygen is in period 2. So as you get to move, when you look at your periodic table like this, okay, so you've gotten helium from that point there, somewhere there on top. You're going the next period where there's oxygen. You're trying to come up with a noble gas electron configuration. So it's in period 2. So you say, okay, I think I've moved from my noble gas there. I've gone to the left part of the periodic table in the new period, which is 2. So I'll pass some elements in the S block. The moment you pass them, you have to show them. You say, okay, 2. Now, as you are moving in period 2, you find that there are no transition elements, meaning that there's no D block there. So you pass it. Then you get to the P. So you ask yourself, okay, helium got 2 electrons. The S block has gotten 2 electrons. So you already have a 4 out of 8. How many are remaining? How many are remaining? You're remaining with 4. But what block are you in? You are now in the P block. So you say 2p. Then how many electrons? 4. So 4 plus 2 plus 2 is what? It's 8. If somebody has got a periodic table, share the periodic table to the group, because zinc, you have to follow it up. I want everyone to understand, because this is very important. We shouldn't just be moving forward, but if you go there, they will just be assessing you. Like you find that your CA is just determined by the first 2 topics, but some of you have gone as far as maybe in the last topic. So make sure you're able to answer all the questions from at least the first 4 topics. That will help you out than doing a lot of things and not having detailed information about each topic. Okay, so get somebody to forward the periodic table to the group just now. There's something that I want to... Anyone who is sharing the periodic table? There's a periodic table that I had shared last time. Okay, check the group. I've sent the periodic table. You can open it. Open your periodic table here. Go to the group and open the periodic table. I don't know if how you... Okay, I'll show it. Don't worry. Let me show it just here. Let me show it. How am I going to show it? Okay, I'm sharing the screen on the different device again. Are you there? Can you see? Okay, so this is what we are saying. If you look at where oxygen is there, you're trying to come up with its noble gas electron configuration. You have to go to the to the period that is above that period. So if you check there, what can you see? There is helium, right, as a noble gas. Okay, so that's how we did it. Now, if you look at where zinc is, where is zinc? Zinc is in period 4. Somewhere in between there. 30. I hope we're able to see. So now if you look at the period that is above zinc, what noble gas is there? What noble gas is there?
Argon.
There's argon, right? Okay. So we're trying to come up with a noble gas electron configuration for zinc. So we'll write the argon. So how many electrons is argon taking away? 18, right? So where we've put argon, it means that we've represented 18 electrons, but we don't have to show, just put argon in brackets. Okay, so we're trying to get where zinc is. So I'm moving from argon there. I'll drop in the next period. Okay, so I'll get where. So what period is it? If you count from hydrogen there, 1, 2, 3, what? 4, right? We are in 4. So I'll show that 4, 4. So as you get to with group 1 and group 2, what block are you in? You are in the S block, right? How many electrons are supposed to be taken by those guys? 2. Not so. Are we together?
Yes, sir.
Okay, so now from the S block we're getting to what block now? We say the block that is between the S and the P is the D. So we are now in the D block, and that's where zinc is. So we're just going to indicate D. Now the question is, what are we going to indicate? Should we indicate 4D? But then the question will come, can 4D surely come before 4P? Doesn't make sense. So if you look at what I was drawing, I was trying to show you ways and means to help you remember. So the moment you move from 4S, you have to go back to 3D again. So you indicate your 3D there. So now it's a matter of counting electrons from where the block is starting from. So we are in 4. Is it 4? Yes, period 4. So after calcium, start counting how many electrons, how many atoms are there up to zinc. So you start counting from scandium. I don't know how you pronounce that. So how many do we have? So it's starting from 21 up to 30. How many electrons are those? Anyone to help us? How many are they? I don't know if you've understood what I'm saying. Okay, or the other possible way of you doing it is add 18 for argon plus the 2 in the S block. It's giving you a 20. So subtract the 20 from the 30. What are you going to have? Okay, 10. So basically that was just a reminder. Now you get to use the noble gas electron configuration. So D block is the only one that like remains a bit behind from the period numbers, but the S and the P go by the period numbers. Are we together? Are we together?
Yes, sir.
Okay. So that was just like a recap of what we talked about. So from there, where did we move to? We moved to now the what? The quantum numbers. Okay. So most of you have left the meeting. Okay. So the quantum numbers. What did we say? Who can give a summary of the quantum numbers what we talked about? Within 30 seconds. Because the idea here is to take things simple, because if you complicate your life, it will be difficult for you to remember. So summary within 30 seconds to help us there with the quantum numbers that are there and what they represent. Or we can go by somebody remembers one, then they give us what it represents.
Numbers there are four. We have the principal quantum number, which represents the size and energy. We have the angular quantum number, which represents the shape. The magnetic quantum number, which represents the what something orientation. I'm not sure of that, but I think it's orientation. Then we have the magnetic field quantum number. I forgot the number already.
Okay.
Magnetic field represents the direction in which the electrons are projecting. Yeah, it's that number.
So you said there are 5?
Four, yeah, my bad, yeah.
Okay. So I don't know if you guys are following up what we are learning, because I don't want to be that kind of a tutor where like you've covered like 4 topics and the students are just like they're trying to find you, but they don't really know what they've learned so far. They can't explain it.
They're following.
S- You're completely lost. So that's the issue of joining late
Same
now.
here, same here.
Okay, you have to pay me for a catch-up class. You can pay me for a catch-up class. I'm not very expensive. Yeah. You can just book me for. Yeah. Don't worry. I'll work on a video to help you catch up. I'll just explain these concepts, I think, within 50 minutes or so. Yeah. Don't worry.
Will be good.
So let's say now you have a principal quantum number of n is equal to 4. Okay. So we are saying that is representing the size and the energy. Okay. So basically what that means is when you are comparing 2 energy levels, one which is maybe n is equal to 3, then n is equal to 2. So what we are trying to say is an electron that is in the 3rd energy level has got more energy than the one in the 2nd energy level. The ones that, so the closer the electron to the nucleus, the lower the energy that it possesses. And this explains the fact why when you are talking about transition of electrons, if they are moving from inner energy levels going outside, you'll find that what they do is they get what? They gain energy. Or we can say they are in an excited state. They'll gain energy. But when an electron is coming from an outer energy level and dropping in, it's supposed to lose energy, because the inner energy levels are able to possess electrons with lower energy. And that's why we say the principal quantum number will tell you about the energy and the size. And with a size, we mean that the energy levels that are far away from the nucleus are bigger as compared to the ones that are inner or closer to the nucleus. That's what basically the principal quantum number tells us. So it's called the principal quantum number because it is the one that is used to determine all the other quantum numbers. Okay. So the next one we said is angular quantum number. So what does it denote? So for the quantum, yeah, for the angular quantum number, which is denoted by L, this one now gives us the shape of the orbitals that we have. So remember we say that for the orbitals we have S, P, D, F. But for the study of our first year chemistry, we will look at SPD more in details. So we said the formula is from 0 to what? What did you say? You can remember.
N minus 1.
Okay, n minus 1. So it will be 0, 1, 2, and 3 in this case, because our n in this case is a 4. So 4 minus 1 will give us a 3. And that's why we're ending up here. So this tells us to say that when you are in the 4th energy level, you have the S, the P, the D, and the F. Okay. So this explains why the energy level number 4 can have a lot of electrons. So the S, remember we said how many electrons? 2. The P6, the D10, the F can have a maximum of how many electrons? 14. So if you add these guys, what are you going to have? 6 plus 14 is 20, plus 10, that is 30, plus 2, 32. So you have 32 electrons in total. And if you go by the formula, which is 2n squared, you plug in there 4. 4 squared is what? 16 by 2, 32. So the quantum numbers prove all those formulas that you work with. Okay. So from the angular quantum number, what did we say again? What point did we make there? We said you go to a magnetic quantum number, which is dependent on the angular quantum number. So this one moves from the negative to the positive of, from the negative to what? To the positive value of L. So each angular quantum number has got its set of what? Magnetic quantum numbers. So for 0, it will just be 0 because there's no negative and positive of 0. So that tells you to say this is one room. So you counting the magnetic quantum numbers, they will give you the number of what? The number of orbitals. Are we together? So the magnetic quantum number tells you the number of orbitals. That's why if you're asking you, the question is asking you to say, given that given a principal quantum number maybe of n is equal to 4, find the number of or calculate the number of orbitals using the quantum numbers. This is the way you get to show it. It's the number of magnetic quantum numbers that you're going to have that are going to tell you how many orbitals are there. So for 0, it's just a 0 again. So only 1. And we said each orbital can only have a maximum of 2 electrons. Okay. So, and we said 0 represents S orbital. Then 1 represents P. So if you go to the P and you want to prove that it actually has 6 electrons, we are moving from its negative. So you say when L is equal to 1, from its negative to its positive, it will be negative 1, 0, and 1. And each number is representing an orbital. So 2, 2, 2, giving us what? We have a 6 there. 6 electrons. You go to the D orbital. From negative 2 to its positive, you have 5, which is a 10. And so on and so forth. Okay, so I think that's enough for the quantum numbers. At least you've remembered something. Well, I've reminded you of something that we we had talked about. So apart from that, what else did we talk about? We started now talking about the formulas, right?
Yes.
Okay. So what did we say? We said the energy of a photon is given by what? A product of what? Planck's constant and what? And the frequency, right? Where V in this case is not representing the the velocity but frequency instead. Okay. Then we also looked at the relationship between if you go under waves, we looked at wave properties, we defined wavelength, we talked about the amplitude and everything else. What did we say? So we say that
So we said
frequency is what? What did we say? Frequency is inversely proportional to what?
to the wavelength.
Okay. So frequency is inversely proportional to the wavelength. This is the way these guys did it. So where there's 1, we had put a constant now, which is the speed of light. So C over what? Wavelength. So if you can get that formula and plug in into that formula, you are going to find that the energy of a photon is going to be given as what? What did we say? You plug in, so it will be hc over what? The wavelength. And this formula works when they ask you to find the energy of a photon when they've not given you what? The frequency, but they've given you the wavelength. So instead of you doing the conversion separately, it's better you just work with that formula to help you and summarize things for you. Are we together? So, by the way, under quantum numbers, we had talked about some principles where we talked about the Pauli exclusion principle, which we said this one tells us to say what? These guys will just ask you direct to say what, state what Pauli exclusion principle. They won't even tell you the topic where it's coming from. They'll just ask you, what does it state? Then you'll be like, ah. So it states at what? What did you say? Anyone who is able to remember what you said?
Each electron at each electron at each position.
You are cutting at the end. You're saying?
Each electron has a different set of all the 4 quantum numbers.
Okay, yeah, that's what we said. Or the other way you can put it, so for him he has used the way of saying each electron has got its own set. Okay, so the other way you can put it is you can say that no two electrons can possess the same set of all the 4 quantum numbers. Okay, it's possible to have 3 same quantum numbers, but the 4th one will be different. Are we together? Are we together? Okay, so how about the other formula that you talked about under wave particle duality? What did we say? So we said that a photon exists in form of what? It possesses wave properties as well as what? Particle properties. So in terms of a particle, when you're referring to something as a particle, you expect that it has got what? It has got mass, right? When you're looking at something with wave properties, you're looking at it having wavelength. Okay, so what formula did we come up with here? Who can remember what we said? So we said you're looking at the energy of a photon being, of course, we started with this formula, but again, if you look at frequency, we've substituted it with what? We've said it's inversely proportional to what? It's inversely proportional to the wavelength. So we can put the wavelength down, and on top we'll put the speed of light. So, okay, so again, we go back to Albert Einstein. Law of relativity. What did he say about the particle? Energy is equal to what? Are we together?
Yes, sir.
So we can look at these guys. We equate them. Hc over the wavelength is equal to mc squared. So 1c can go away. Or you can no longer see the screen.
Yeah, it's not seen.
What has happened again?
Not me, I can see.
You can see.
Yes, sir. Not for everyone.
How is that possible? Okay, let me try to start sharing. Let me restart it again. Okay, it's still being shared. I'm restarting it again so that it appears to everyone. Can you see now?
Yes.
Okay. So this is the formula that these are the formulas that we are talking about. So we are looking at the wave properties of a photon. We looked at this formula. As I'm sure it's one that we are just from talking about. Then the famous formula of Albert Einstein as well. So when you get to equate these guys, this is what we are having. So the C will cancel out on one side, on both sides, because it's common. So by wave particle duality, they can ask you what it means. So a photon possesses both properties of a wave and a particle. Okay. So we are remaining with h over what? The wavelength is equal to mc there. So basically, our goal is to make wavelength a subject. So wavelength is going to be given as what? So if you make it to be, so if you close and multiply, this is actually going to go there. So you have to divide by the MC. So it will be h over that. So remember, if you go back again to the formula that we are talking about, the issue of looking at the properties of the relationship between the wavelength and frequency, what are we saying? We're saying that the frequency, I'll use that so that you're able to connect, and the wavelength, these guys are what? They're inversely proportional. Okay. So, in other terms, in our textbooks, you're going to find that the frequency is going to be velocity over what? Over wavelength. So whether they put speed of light or the velocity, it's still the same. So I can change this formula to make it general so that we don't just focus on the speed of light. We can look at anything that possesses mass. So it will be h over mv. So again, that's final. So this equation is called what? De Broglie equation. Are we together? It's de Broglie. It's this guy who came to combine this formula, these formulas. So it's de Broglie. So when they ask you to say calculate the de Broglie wavelength, you have to work with this formula. Are we together? So this formula can also be summarized. For the people who've already studied momentum, we can put momentum there, because momentum is a product of mass and what? And velocity. You don't necessarily have to know it, but you can just know this for now. You learn it later in physics. Are we together? Okay. So what else did you talk about? What else did you talk about? Photoelectric effect. Okay, I think photoelectric effect. Okay, so it's a quick summary of what we said under photoelectric effect. What did we say? We said that what is it basically? How would you describe photoelectric effect? Okay. So, of course. So, what are some of the things that makes it possible for the metal surface to emit electrons? So, basically, what we're having is we are saying, some of these things should even be picture it. So, you have light coming from a certain direction. Okay. So, and this is a metal surface. So, you find that will be emission of the photons. So this is what we're calling spontaneous. This is what we're calling photoelectric effect. It's being the spontaneous emission of photons or electrons by a metal surface when light. So what we are saying, this is our light. Then what is being emitted is photons. Are we together? Okay, so we looked at some of the things that are very important there. Is it always that when light strikes a metal surface, there will be emission of photons?
No, sir. It's
Okay. So there's a minimum frequency that is required. We know light possesses different frequency. So there's a minimum frequency that is required. So only a certain light that has the minimum frequency required, and the minimum frequency that is required is what we call the threshold frequency. Okay, this is the minimum frequency required for electrons or photons to be emitted from a metal surface when struck by light. Okay, are we together?
yes.
What are some of the points that we had noted? Let's say that the rate that we have has met the threshold frequency. It has frequency greater than the threshold frequency. So what happens when we increase the intensity of light? in such a case?
The direct proportional to
So you are telling us you're telling us a relationship. Now, when we increase the intensity, tell us what will happen.
more electrons will be emitted.
Okay, more photons will be emitted. Thank you. What? So the same applies if you reduce again. You expect that photons being emitted will also reduce. Okay. What else did we say? How about if you're starting? Okay, so we interchangeably use it too. Yeah, you don't have to worry about that. Okay, because these guys are kind of massless, so they are one and the same things. But of course, not all. Not every case when you're referring to an electron do you refer to a photon. So what happens if you increase the frequency of light? What do you expect?
So you said something like to increase the frequency of light, but yet it doesn't achieve the threshold frequency. No electrons will be emitted.
Okay, so that is in contrast. So in a case where you have something below threshold frequency, light of frequency that is below the threshold frequency, whether you increase the intensity, nothing will happen. The electrons will still be there. There'll be no emission of photons. That's what we said. Then how about the issue of increasing frequency? What did you say? What did you say?
So the electrons also emitted from that.
Okay.
Maybe another.
Yes, you can add on, but I think I'm not agreeing with what you said. I've just said yes for no reason. Why have I said? Oh, it's the same? Maybe. Uh, no, some of these things you get.
If
Y-
if you've increased the frequency and then like the frequency is already you already achieved the threshold frequency and then you continue increasing, the extra frequency will be used for movement as kinetic energy.
Okay. Okay. So, and that's what it reads to this formula, right? That now brings in the issue of this formula. Okay. So now the extra energy will be used as kinetic energy. Okay. So meaning that, and in this case, what we'll do is, if you are working with this formula, the V naught there is the threshold frequency, right? So if you subtract now, you have now have a new frequency that you've increased to. Okay. So if you increase the frequency now, you are subtracting the final frequency multiplied by the Planck's constant minus. So it's like this part is representing the energy that is just required to make it possible for emission of photons to be there. But then the extra or the difference in energy between the new frequency and the initial one is going to give us the energy that is going to reach to what? The kinetic energy, which will reach to the issue of photons moving. So know this formula as well. And I think this is a formula that you can work with. I don't know, Maynard, if you said you had the question. So look at this formula. I think it can help you out.
Yes, I think so.
Yes. Okay. I think let's there's just one concept that just want to talk about for today. Um and that will be the end of the topic. So within 5 minutes or 6 we should be done. Okay. So we've not learned anything new so far. It's just now we just remained with a small part that I was supposed to talk about. By the way, there's also this formula that I've not reminded you guys. We talked about wave number. We said wave number is given as what? 1 over what? Okay. So they ask simple questions like that. They just say calculate the wave number. then you're lost. What's number? Yeah. Okay. So now we said we're supposed to talk about transition of elements, the issue of electrons moving from one energy level to the other. What happens? So remember, I said whenever something is going outwards, an electron going outwards, we said, what did we say? We made a point to say, is it loss or gain of energy? I've talked about that.
Gain.
Okay, it's it's gain of energy. Okay. So now, things associated with these calculations under transition of electrons, I talked of a formula that can help you to find the wavelength. Okay. So there's a formula that can help you to find the wavelength of a transition of the electrons as they are transitioning. It will help you find the wavelength. Okay. So we talked about Liebig's equation, and I gave it to you guys. Okay. So it's very easy to remember this formula, because what is there is all you're going to have is going to be 1 over the wavelength. Okay. And this is supposed to be equivalent to what? The Liebig's constant itself. Then in the brackets we always have the same things. So it's just the issue of 1 over the final subtract what? So this is actually a two-way thing. Whenever you interchange, so whenever you're starting with a final one, make sure that most of the cases what you have is you have a negative in front of a formula there. Okay. Put a negative if you're starting with what? If you're starting with a final, and that would be my advice. Start with a final so that you don't confuse this equation, because there's another equation that you have to work with. Remember, I said there's also another equation that can help you to find the energy that electrons are possessing while they're transitioning, the change in energy while electrons are transitioning. So we said the change in energy was going to be given by also this formula, negative 2.178 by 10 to the power negative 18. Again, in the brackets, you have the same thing, 1 over final, then 1 over any initial square there. So in the brackets, we have got the same thing. What we are calculating is different. In the first equation, what we have is we are trying to determine the energy. Okay. Then we are starting with a negative because we are starting with a final one there. The same is applying. If you start with a negative, start with a final one there. So don't use them differently. You are going to confuse yourself. So just
So, sir, in short, can we just like without just writing the energy, then after plugging determine the time of the
no. You'll be wrong. Because like the formula is supposed to give you it's possible that the answer can be positive and negative depending on what you're talking about. Okay, are we together? So I can give you an example.
yes,
Like what I was saying when something is moving from maybe energy level number 1 maybe up to 2, is it loss or gain of energy? So this is the way questions come under transition. They'll tell you an electron moved from n is equal to 1 to n is equal to 2. Calculate the energy associated with this transition. What would you say? You have to go to a formula, right? Of course, that is a constant. Let's forget about it for now. Let's focus on the brackets. In the brackets, it's going to be 1 over what? The final one is what? 2 squared. Minus the initial one is what? 1. So you have 1 over 4 minus 1. Are you going to have a positive value or a negative? 1 over 4 minus 1.
a negative, sir.
So the negative multiplied by that negative, if you multiply it with that negative on top, is it going to be positive or negative?
Positive.
So it tells you that as you are moving from 1 going to 2, it's what?
Gain of energy.
It's gain of energy because it's positive. But if you reverse this, you are going to have 1 minus 1 over 4. If you are moving from 2 going to 1. So you are going to find the negative answer, which is going to tell you that there was loss of what? There was loss of energy in such a case. Are we together?
So, sir, the negative 2.7,
Okay, I wouldn't say it's a constant because it's something. It's a formula that is derived. Okay, but no, it has a constant in that formula. It's not a negative value, because if you want, you can take it to be positive and reverse that part. You say one initials, but I don't want to talk about two contradicting things. So let me just teach you one approach. It's a negative like that.
So it's always there,
That's what I'm saying is this. If you go in a textbook, you find it's positive. Of course, they are not textbooks, unless if you get zoomed and. But then, if you find it to be positive, sir, this side is going to be the opposite. It's going to be initial instead minus the final. This is the way it's working. Okay, so you consider it to be positive, you reverse what's in the brackets.
Oh,
Yes. Okay. So there are questions where they ask you to find the wavelength associated. There's two ways of approaching that question. It's either you find the energy. After finding the energy, and this is the way that I think this is the approach that I used to use most of the times. I would find the energy, then I would go to this formula again. So I know what's on top there on this formula. All these are constants. So I'll be able to find the wavelength since I have the energy with me. That's the way it works. Oh, you can use Liebig's equation now. Whichever is easier for you. But this one is more easier in a question where they don't ask you to find the energy. When it's just direct to say find the wavelength, it's better you just go to this formula directly. So, yeah. Because all you know is in the brackets you have got the same thing. What's different is only what is here. And for this one, it's a constant that they even give you. It is a constant that they are going to give you, right? Okay. So you don't have to worry about this one because they will give you. Are we together? So this is Liebig's equation. Are we okay?
yeah, yeah.
Then I think last time we talked about the question where they said to say what series is this kind of transition. So basically I'll start with the issue of this. Usually we get to talk about this whenever you are moving from n is equal to 1. Okay. Not really, let me not put it moving out, but as in let's say this is n is equal to 1. Then we talk about n is equal to 2. Maybe n is equal to 3. Okay. So whenever you have electrons coming from outside up to coming into the energy level number 1, these have got series. Okay. Again, they have different names. So for n is equal to 1, we call them Lyman series. Okay. For the second one is Balmer series. The third one is what? It's pass chain. So with time the more you get to do more questions, you get to know these brackets. And for the sake of A-level studies, you have to end on the number, the fifth one, which is going to be P funds. Okay. So whenever they're asking you to say you have a transition of electrons from a certain energy level to, so the final point will tell you the series that you are dealing with. Okay. So now these are associated with different what? They are associated with different frequencies. Okay. So if you go to the spectrum there, the one with the highest frequency is what? Okay, forget about the Y-rays and the X-rays. So we'll start from ultraviolet. So Raman is associated with UV, ultraviolet. Then the Balmer is associated with visible light. The pass chain going up, it's infrared. So it's very easy to remember that. Whenever they ask you to say, okay, you have a transition of elements of electrons from maybe n is equal to 4 going to n is equal to 2, what, so they will ask you the for something that is part of the spectrum which is actually associated with such a transition. Okay, is it infrared? So what light is associated with this and that? Yeah, you'll be able to tell by looking at the transition that is ongoing there. So these are the basic things that you are required or expected to know under this topic.
So you say that from n equals to 3, what?
Not from, I'm not saying from, but I'm saying to. Whenever you're coming outside, you get to n is equal to 3. It's past chain. But like, okay, like going up, or you mean the spectrum? It's the infrared if you're talking about the spectrum. Infrared, like all the others going up. We don't get to talk about the other things. We only talk about these three: ultraviolet, visible light, and infrared. Okay. Do you have questions? Do you have questions? There are no questions? Do we have questions? Okay. There's this question that I think they like asking this question a lot of times. Okay. Because this question doesn't specify. I think that's why I wanted us to solve it. It doesn't specify. Where they specify, it's very easy for you to be able to do what? It's very easy for you to be able to find, like, get to find the energy associated with that transition and also the wavelength. Now, where they ask you to say find the change in energy where they are dealing with hydrogen. Okay, so the question usually says calculate the energy required to remove an electron from a hydrogen atom. Have you gotten the question? So they'll ask you to calculate the change in energy associated with or the energy required. Actually, we can put it as the energy required to remove the electron, to remove an electron. Of course, an hydrogen atom has only an electron, a single electron. So the amount of energy required to remove such an electron from its ground state in a hydrogen atom. So the same formula that we are working with, we'll say negative 2.178. This was by Bose. So this is usually called Bose equation. Okay. So you say 1 over n final squared minus initial, right? So if I ask you a question to say how many energy levels does hydrogen have, how many does it possess? From what you know. To start with, how many electrons does it have? Wow. This is so funny. Okay, so you find that basically the number of energy levels that hydrogen has, they are just it's just one. Okay, so it's one electron there. So that one electron, how is it going to move now? So it's moving from an energy level initially of so the initial one is what? It's 1. Then the final one is we don't know, so it will say infinity because it can just be going. So if you get to plug in there, you have negative 2.178 by 10 to the power negative 18. So the final one is 1 over infinity because we don't know where it's going. Then the initial one, it was 1. So 1 over 1 is just going to give us 1 there. So remember, we are squaring the squared. So squared, then there it's 1 squared, will still be a 1. Okay. So what you have in the brackets here, we have 1 over infinity squared minus a 1. So basically the infinity squared, this is something that making this to be a 0 in just, because infinity is a very very big, but if you get to divide into the 1 there, you don't expect it to give us a bigger number. It is, we just consider it to be a 0. So if you multiply the negative 1 with this, it will give you an answer of 2.178 by 10 to the power negative 18 joules. So this is usually the answer. Okay. And I think from the basics that we've talked about, it marks the end of our topic.